So, once again, good afternoon to one and all. Welcome to the fourth discussion session for the NPTEL course titled Physics of Nanoscale Devices. I'm Jyotishwaran, a PhD student from the Electronics and Communication Engineering Department of IIT Roorkee. So, let us begin today's session. So, first, I'd like to ask if there are any questions or queries from the two live attendees from the previous
No,
week's
sir.
content. No questions. Okay.
Good evening, good afternoon, sir.
Yeah, good afternoon.
So, from my side, actually, I have attended week 4 lecture completely and
Yes.
also understand how we can calculate the current for two
Mm-hmm.
terminal devices
Okay.
with the exclusion of gate. With the exclusion of gate. So,
Yes.
sir, my question is like that do we have any questions like to solve the current value, like some numerical like
Ah,
that?
okay. So, so far, so week five has been unlocked, right? Like week five
Hmm.
videos are available to you guys, right?
Available, sir, but not started yet.
That is fine. That
Week
is fine.
5.
So week five and assignment five is open to you guys, right?
Yes, sir.
Yeah,
Open.
it
Yes,
has
sir.
gone live. All right. So very good. So I can scroll through the week five assignment, and as you can see again, like there are some numericals, but you'll see that we are actually not having any current calculation type of questions because
Okay.
ultimately, in order to discuss those things, like we will have to get more uh, into the details of like. Okay, so let me quickly start with the writing part. So now we were considering what we are looking at. Um, uh, oh, okay, that makes sense. Just one second. Yeah, so we are looking at essentially current
Sir,
in a.
whiteboard display.
Oh, it's not visible. Yes, thank you, thank you. Uh, Let me start sharing my entire screen. Um, and it should be visible now. Correct?
Yes, sir.
Yeah. So we are
Yes, sir.
considering current in a ballistic channel. So what are the terms we see when we write the expression for the current? What we'll essentially see is we will have d of e. So on the outside we will have 2q upon h and d of e to f2 minus f1. Care to tell me what other factors will appear over here?
Slide is not opening, sir. Actually.
Okay, try to tell from your memory
Yes,
in
sir.
case the slides are not opening.
It's okay.
And this part will also tie in with today's discussion. And in today's discussion, we'll actually be doing some numericals. So
Yes, sir.
I'm deliberately missing something. I want you guys to identify and tell me what that something is. The answer is in the slides. Please, if you can, quickly.
Okay.
just to be exact. Let me see.
The final equation is like 2q upon h bar integration of gamma
Uh-huh.
e pi dE
Uh-huh.
by 2 f1 minus f2 dE.
Yes, very good. So, what is F1 minus F2?
Sir, actually, it's Fermi level of source and drain.
Yeah, so that's what I've written as Fs and Fd here. Okay, just to
Yes, yes, sir. Yes.
times pi.
Yeah.
Correct. So, yeah, just one second. Bar has overshot. Yeah. So this should be the expression. Yes, times dE. So now this is the expression for current for a ballistic channel. So depending on the dimensionality of the channel, which quantity will change? Can you tell me?
Sir, DE.
dE, sir, density of effects.
Uh-huh. Will anything else change?
Sir, already we considered na like for source and drain are of bulk nature. So
Yes. Uh, sure. So D, of course, will change with the dimension. What about gamma E? That's my question. Will gamma E change with the dimensionality of the channel? What is gamma E, by the by? Can you guys answer that question for me?
modes, sir, modes.
Gamma E is modes.
No, no, no. Through that, we'll go for modes
Yeah, so
analysis.
what is gamma E? Like, so what does gamma E signify?
Okay.
Oops, why am I unable to draw a simple arrow mark? I drew it perfectly well in the previous case. My God. I'm sorry, I'm just acting a bit obsessed. Mm, yes, this will have to do. So this, what is this quantity called? It has a name. I mean, of course, it has a name. Are you familiar with?
Broadening of energy levels.
Yes. So what does broadening mean? So we shall start today's discussion from that, and hopefully I'll also try to give you some pointers towards the week 5 assignments as well, as always. But we shall do that through certain numericals. That is why you see that today I'm not even using any PPT to talk about the topics or anything. I'm just diving right into it. So what effect does broadening correspond to? Is it a classical effect? Is it a quantum mechanical effect?
Sir, it will be a quantum mechanical effect.
Uh-huh. So okay, if it is a quantum mechanical effect, then can you tell me what principle of quantum mechanics? Like, so in density of states, we know that that is technically to account for the number of energy states. So that is the quantized energy levels. I know the Fermi function is essentially over here. It should be noted that the Fermi function plays two roles. First, it gives me carrier statistics, and the difference in the Fermi level is also, in a way, you might have seen in week four's lecture itself. Just give me 1 minute, please. I'll be back. Yeah, so I'm back. So in this Fs minus Fd, we will also have the information of the potential difference. Have you seen this in the lectures already?
Yes, sir.
Yes. So can you quickly tell me when that will happen? Like how that will show up?
Yes. So first, in case when we take some two different material in the source and drain, then
Yes.
there is a possibility of potential difference at the source side and the drain side.
Uh-huh.
And in the second case, when we apply voltage in the drain side, then there is a potential difference occur between the source and drain side.
Yeah. So how does that appear
And
in this term? That's what I'm trying to ask. So have you come across this quantity known as the Fermi window function?
Fermi window.
Yes, in the lectures.
Uh,
No, sir.
Not yet?
no, sir. Fermi window, no.
Just let me check. I mean, maybe I've jumped forward a week. No worries. Uh, so in week 4, if we look at the general model, because the general model of transport ought to have conductance values. So you have this, you have this. Okay. Aha. All right. So wonderful. That has not been covered, which is a very good thing for all of us. It has it not been covered? Let us be doubly sure, triply sure. We have one more attendee joining us. Yes, please. Yeah. So, okay. So, week 5, is it getting covered? Uh, it's part 2. Amazing. Okay, so that thing probably appears in week 6, and that is a very, very good thing. So do not worry about the Fermi window function right now. It is, you will encounter it eventually. So coming back, um, yeah. So yes, for now, understand that Fs minus Fd gives us information of the carrier statistics. Oops. Uh, the board is visible, right?
Yes, sir.
Yes, sir.
Oh my God, like, fine, but please vanish. I don't want you. Yes. Huh. Okay. So this potential difference part, let me switch to black and write covered later just for the sake of clarity. So explicitly, like if I apply a potential V, potential difference V, will that appear in this term? The answer is yes. And how it will appear is given by that quantity known as the Fermi window function. Do not worry, it will appear, and we will do enough mathematics with that quantity. Um, so this is the second quantum mechanical property. Now, what does broadening correspond to? Like what quantum mechanical aspect of conduction does this third term correspond to? Like we are essentially looking at this integral term by term. So what is this third term? Like this is a constant and this is the variable of integration. So if we understand this, then we have actually understood the ballistic model of transport. So What does broadening mean? Like why? Okay, like forget quantum mechanics. What does the word broadening mean? Can you tell me? Any
Sir,
of you?
to increase in any dimension.
Fine, very good. To increase in some, dimension to become like, what is the opposite of broad? The opposite of broad is narrow. So let me,
Hello.
yeah, yes,
Yes, sir. Sir, actually, this broadening comes like one thing sir told about transit time.
yes.
Yeah, transit time is like the hopping of charge carrier from source to the
Mm-hmm.
channel and
Mm-hmm.
how long it takes to complete that channel length. That is also included in that transit time. So if the transit time is very less, then because of
Uh-huh.
that some broadening relation is there, sir.
Okay. Good. You've been paying attention. Very good. That is the explanation. But let us try to move to more basics so that of course you guys will benefit from the discussion, and people who are listening in to the recordings will also benefit from it. So yeah.
Yes, sir.
So yes, as you are mentioning, yeah, now if you remember in the classical model of conduction that we do, there is a time quantity. That quantity is called tau. And what is tau for classical? Oops, just one second. Yeah, so my whiteboard calibration seems to be a bit off today. So this quantity is called relaxation time in for classical conduction, essentially for what shall we call it? Uh, what shall we call it? Let's just call it classical itself. So this quantity is,
Sir, whiteboard is not visible.
is it not visible? Okay, let me reshare. And yeah, the new attendee seems to have bailed out. Um, yes, it should be visible now.
Yes, sir.
Yeah, so we have this quantity tau, which we call relaxation time. What does relaxation time tell me in the classical model of conduction?
Sir, time between two successive collision of an electron.
Uh-huh, very good. So, of course, when we are trying to analyze the conduction of electrons, a certain time element has to be considered because electrons are moving from point A to point B. As Kamal pointed out, what we have is essentially this kind of a setup. So I have my source, my drain, and my channel. So too big. Yeah. So I have my source, my drain, and my channel. Okay. So an electron has to enter this channel and then move along this direction and reach here. So that is the process of conduction. So there is a sense, not a sense, there is a very definite motion that is occurring here. So since there is a motion that is occurring here, it is fair to assume that the electron was here at a certain point in time. Then it spent a certain amount of time. Let us call that time for now. Let us call it, in fact, can I switch colors? Uh, you know what? Yeah, since I've already written it, I'm going to get rid of the relaxation time because we are not doing classical theory. That is just to talk. So now In this model, what happens is it spends a certain time in transit. So I have what is known as a transit time. Okay, so need to erase this slightly. So, so I have a transit time. Now this transit time I'm going to call again as tau. I mean, it's the same notation that is, yeah, my taus don't seem to be that good. Yeah. So this is the quantity we are referring to as tau. Now tell me what happens when a particle in quantum mechanics exists in an energy state for a finite amount of time. Can do either of you know what happens?
No, sir.
Okay, no issues. I mean, that's my job to tell you what happens. So, are you familiar with this relation? Are you familiar with
Yes,
this
sir.
relation? So, what is this?
The uncertainty principle.
Yes, but uncertainty principle
Yes.
with respect to what? It's the energy time uncertainty. Like
Energy and time.
typically, we write uncertainty as x and delta x and delta px. But here,
Yes, sir.
of course, we are considered with the energy time uncertainty. So, what does this mean? It means that if T is of the order h bar, so this is the energy time uncertainty relation. So, that is this quantity. So, what does this tell me? Let us say I want a very well defined energy level, a completely accurately defined energy level. In that case, the quantity delta E has to be what? If I want a well defined energy level.
For discrete energy level.
Yes, for a discrete energy level, if I want one exact value for that energy level, what will delta E be for that energy level? What will the uncertainty of that discrete energy level be?
Sir, zero.
Very good. It has to be zero. But this relation always holds. This is a quantum mechanical relation. So if delta E goes to zero, then what happens to delta T? Delta T will shoot up to infinity. Can you see that?
Yes, sir.
As delta E becomes smaller and smaller and smaller, delta T will become larger and larger and larger. Okay. Conversely, if delta T is small, then delta E will be large. So, what happens here? Remember what we discussed last week. Last week we discussed that essentially I have a bulk system and I have discrete energy levels in my channel and I have another bulk system. So this is my source drain channel model. Uh, yeah, discussed in the previous week. So essentially an electron starts here, jumps into one of the available energy levels and jumps out of that level to go into the drain. Remember?
Yes, sir.
Okay.
Yes, sir.
So in this discrete energy levels, now my electron, because of this transit time, is now spending only a finite amount of time. Because after
Yes, sir.
that time,
Right.
this electron has moved from the source to the drain because conduction is taking place. Therefore, we have to write delta E times tau is equal to h bar. I mean, this is of the order. Typically, we consider it as equal to h bar. So we write this, and then we can say that delta E is h bar by tau, where of course the tau, as we have defined before, is the transit time. Okay. So now do you
Yes, sir.
see what this quantity delta E is? This essentially tells me that because I am spending a finite amount of time here, this energy level is no longer a well-defined energy level, but this will kind of become broadened. There will be an uncertainty in it. Similarly, for the energy level below that, there will be a broadening. And similarly, for the energy level above that, there will be a broadening. Now, what will that broadening depend on? The broadening will depend on the transit time. If the transit time depends on the energy of the particle, then the broadening will correspondingly vary with the energy. If the transit time does not depend on the energy of the particle, then the broadening will, not depend on the energy. So this phenomena is what we refer to as broadening. And this delta E is therefore directly written as gamma of E. Is that part clear now?
Yes, sir.
So essentially what happens is we have this factor of h bar over here. So in moving those factors in and out is how we end up with this quantity 2q upon h bar on the outside. Did Professor Vishwendra define what 2q upon h bar is? It has a name. Did he tell you what the name is? If not, we'll come to it later. That's why I'm asking.
Don't remember right now.
Don't remember right now. Okay, fine. Go back and see the lecture. If it defines it, you can see it. And of course, this quantity will come back again and again and again. This is a very important quantity.
Sir,
Yeah.
yeah. Sir, in that current calculation, sir told that
Yes.
all the value we can find with we get some value, but that gamma in
Uh-huh.
for that we have to go for the mode calculation.
Yes. Indeed, you're
Other
correct.
than that, all values are constant. We can able to find it.
Yes. So now do you see why that is the case? Like, do you understand why Professor Vishwendra said that?
Yes, sir. Yes, sir. Understand, sir.
Yeah. So yes, because Fs and Ft, these are known functions. I know what the Fermi function is. So these are predefined. The density of states depends on the geometry of my channel. This is the only quantity that is the unknown variable because that essentially depends on how much time my electron is spending in the channel. So now tell me what happens here. If the energy level gets broadened, in a sense, electrons having multiple energies can now enter the channel. Is that clear? Previously, what happened? If you remember our last week's discussion, I told that the energy has to exactly match for the electron to
Yes,
jump in.
sir.
Now that is actually not true. So last week I was not being totally honest with you guys. The truth is the energy need not exactly match with the channel. It can be somewhere in the neighborhood depending on this broadening quantity. Okay. So those are the three effects, and all these three effects, as you can see, have their own individual quantum mechanical basis. So this entire model of transport that we are talking about here is, it's not a completely quantum mechanical treatment. It is a partially quantum mechanical treatment, but it is a quantum mechanical treatment of conduction. So this model of conduction was due to Rolf Landauer. So that is why this equation, if I'm right, is called the Landauer current equation. So that is an added piece of information. So this is the first part. Now we shall move on to what modes are. So yeah. Now yes. So modes in a ballistic channel. This part will be covered in detail in week 5. So just remember these things and keep it in mind when you are going through the week 5 lectures. And in the meantime, if you guys have any questions from the previously covered syllabus, like even from week 1, 2, 3, 1, 2, and 3, please feel free to ask. Like again, I reiterate, the primary aim of these sessions is to clear and clarify your doubts. So yeah,
Sir, your previous recording is also available na, in the site.
it should be available. Like a
Okay.
YouTube playlist, because I've already made it. So that link should be shared with you guys. If it is not, like,
Yes,
have
sir.
you received any link?
So for your not.
Oh, okay. In
Actually,
that case, okay.
we got
Let
for,
me let me do one thing. Have you gotten the links
yes.
for some other discussion session?
Discussions are like numerical solving problem session. In that
Okay,
one Excel sheet is there and their link is pasted over there, but not for
okay.
your lectures.
So, like for this course, are the links being uploaded by somebody else also?
Yes, sir.
Oh,
Right,
good,
sir.
good, good, good.
Yes, sir.
Okay, so mine is not getting updated. Okay, so let me check with them. If not, I will share the link with you guys after this session directly. Okay, so
Yes, yes.
all right. Um, yeah, so coming back, we have our current expression. Now I'm going to rearrange the terms a little bit. Yeah, I forgot to put the constant. So H. Yeah, no, this is how you would have seen the expression in the slides. F2 minus F1. Of course, F2 and F1 are function of energy. So this is how you'll see it. So now this quantity right here, this complete combination of the broadening and the density of states. So essentially, what information is does do these two terms contain? It contains the information of the number of energy states and to what extent those energy states have been broadened because of the finite transition time. So these two terms together give you what are called the modes. So in general, we can write this expression as 2q upon h integral. So the modes are called m of e. So for a ballistic channel, we can write it as m of e f2 minus f1 d. And that's it. Have you seen this expression in your lecture so far? I think up to this point it must have been done in week 4.
Yes, sir.
Yeah. So up until here, we are good, correct?
Yes, sir.
So now, yes, let us try working out what the modes in a ballistic channel for, say, 1D channel. Let us take the simplest example and consider the modes in a ballistic channel for 1D channel. So, and that should help us move forward. So now we are looking at modes in a 1D ballistic channel. So what is D of E for 1D?
Sir, G of E into L.
Okay, so I'm asking what G of E is.
Sir, density of state.
Yeah, for a 1D channel, like give me the expression. You should know that by now, like you've solved assignments. I've written part of it. Just tell me what goes in this part.
I think, sir, for 1D, it's inversely proportional of energy, like.
Okay, give me the terms. Shouldn't be that difficult.
Okay.
Root over M star by
Uh-huh.
2E.
Very good.
मतलब into 1 by pi h bar.
Yeah, I have already written that. So good. This is our density of states. Fair enough. Uh, now let us consider
Right.
a system. Let me use a different color just to emphasize that it is a figure. And I have a 1D channel. So this is, so what kind of an object can be treated as a 1D channel?
Sir, carbon nanotubes.
Uh, Kamal, do you agree with that?
Quantum wire, sir.
Uh-huh. Would you agree that carbon nanotubes can be treated as a 1D channel?
Carbon wire. Yeah.
No, I'm
Thinking,
asking.
sir.
Yeah, think please. I mean, by all means, thinking is good. Thinking is, good for your health. Yeah. So, so yes. So the other attendee is Ichanshu, right?
Yes, sir.
So yeah, you're correct in saying that carbon nanotubes can be treated as a 1D channel to a very great extent. Yes, they can be. However, we should remember that it is actually a 3D object that is, very large in one dimension and very small in the other two dimensions.
Yes, sir.
So in
Right,
that
sir.
case, what essentially happens is it becomes as what is known as a quasi 1D channel. So it is a 3D
Yes,
object that
sir.
has to be treated effectively as a 1D object. So that leads to certain additional phenomena which we shall be covering in later weeks. Okay. So right now the best candidate that we have is something like a nanowire. Okay.
Mm. So yes, sir.
Just a string of atoms, a tiny little string of atoms that now you can ask, but the atoms are three-dimensional objects. Shouldn't I consider that? Yes, in principle one should, but that is the best we can do. I mean, we cannot have objects smaller than an atom in an electronic device. So that is as close to a 1D object as we can get. If we can build a real or if we can have a single real or a virtual atom, then it has to be treated as a 0D system, as a quantum dot. Okay. So in this case, if we have nanowires, we can treat it essentially for all intents and purposes as a 1D channel. Carbon nanotubes is a very good answer, but those are quasi 1D channel and they have an additional property, a very important additional property which we shall see in the coming weeks. And lots of questions will be asked about that as well. So now, tell me this. In this 1D channel, what is the transit time? How do we find transit time tau? Because I know gamma, oops, let me change the color. We know that gamma of E is equal to h bar by the transit time. So how do we find the transit time? Any hints? Any thoughts?
Sir, the time the electron takes from moving from source channel contact to drain channel contact.
Uh-huh. Okay. So how do we determine that? Of course, you've defined the quantity. Now I'm asking, how do we calculate it? Yeah, so let us also say that this channel has length L. That should serve as a hint. There is a factor of L over here also. So tell me this. If I know the velocity of the electron in the channel, can I find tau?
Yes, sir.
Okay, so let me say the velocity of the electron. Let me write this separately. Let V be the velocity of the electron. Hmm. So if I know V, now can you tell me what tau is?
Yes, sir. L by V.
Yes. Is it L by V? Read this statement exactly. I've said V is the velocity. What is velocity? Is it a scalar or a vector?
Sir, vector.
It's a vector. So, which direction is V pointing in?
Sir, if we take this L on the x-axis to be x-axis, then we will
Uh-huh.
pointing towards positive x direction.
So, yeah, let me call this the x axis. Remember, the channel is a quantum mechanical channel. Now, in a quantum mechanical channel, what is the behavior of my electron? Is it particle behavior or is it wave behavior? Go back to week one, or your basic quantum mechanics or whatever.
Sir, wave nature generally happens when that size is like zero point 0.1 nanometer something. 1 nanometer like.
Yeah,
But
so
here
this
for
is a
ballistic it's 10 nanometer something length, channel length.
Uh-huh. Okay.
So for that, you told like particle or wave nature. So here particle.
But not entirely particle. Some quantum aspects are still there. That is why this is not a complete bulk channel. This is still a ballistic channel. What does ballistic mean
Yes.
in this case? There are no collisions or interactions or scattering inside the channel. Like whatever velocity my electron enters the channel with, it stays in the same velocity until it reaches the drain. So essentially, what happens
But sir,
here?
one thing.
Huh?
So one thing is like that the interface of source and channel between source and channel and the interface between channel and drain.
Uh-huh.
There is some interference at that side, na?
Yes.
Between the interfaces.
Yes.
So
So
because
yeah,
of
you
that, maybe some collision, some loss.
of course. And outside of that, there can also be some reflection.
Yes, sir.
Like in essence, an electron can be bouncing back and forth between the source and the drain. That is very possible. That is what you're supposed to understand here, because only if an energy level is empty, freely available over here, will an electron jump into the drain. Otherwise, it cannot jump into the drain. Because unless and until that energy has been supplied, the electron cannot make that transition. So in general, we can be having both positive x direction and negative x direction. So on an average, it is reasonable to assume, like, now this is an assumption. We assume that velocity, the direction distribution of velocity is uniform. So this is an assumption. Uniform directional distribution is assumed. So in that case, what fraction of the electrons will move in the positive x direction? Like how many directions can the electron move in a 1D channel?
Yeah. Either
Huh?
left or right.
Yeah, so there are only two directions possible. Now I'm saying the direction is uniformly distributed. So how much of the electrons will be moving right? The right is the thing that we
So the
need.
half of the electrons.
Half of that, very good. So ultimately, what we will find out is that if we, or let me say for clarity's purpose, because I've already named the axis here, let me call this Vx, then we will find out that this quantity Vx plus, which is the average positive velocity, is equal to Vx by 2. Is this clear?
Yes, sir.
Which implies tau is equal to L by Vx. Oops. Vx by 2, which is equal to 2L by Vx. Therefore, using this over here, I can write this as h bar by 2L times Vx. Is this clear?
Yes, sir.
Now, again, what is Vx? Can someone tell me what is Vx in terms of the energy of the electron?
So this we can find out by um, relation of kinetic energy.
Yes, very good. So
uh,
kinetic energy E is equal to what?
half mv square.
Very
And
good.
here
Half
we
M.
will take m as effective mass.
Of course. So what is Vx?
Root over 2 times of E by m star.
Brilliant. So I will substitute that over here. Ultimately, we have square root of 2 E. You'll see that there is a nice conspiracy of terms happening here. Why did I just redraw the same square root symbol? Yeah, 2e upon m star by 2l. And this is capital D of E. Now, what did we say modes were? Gamma by 2 pi dE. This whole thing is my modes. Now we have calculated gamma and we are here. Oh, I was supposed to open a new board. Yeah, what is happening? Okay, just 1 second. Yeah, yes. So modes. So what is M of E? M of E is gamma of E. Oops, is gamma of E by 2 into pi into D of E. And what is gamma of E? As we had previously seen, it is h bar square root of 2e upon m star divided by 2l into pi into 1 over pi h bar square root of m star by 2e. Yeah,
Yes, sir.
so can you calculate this product? Of course, into L, uh, because this is not G of E, this is D of E into L. So come on, this should not be that difficult.
Sir, 1 by 2.
Yep. Wait. Let me quickly just go back. What did we write? Gamma of ES. Oh, okay. So there'll be another factor of 2 because I need gamma E by 2. Yes. That's what I was missing. So half into this quantity. So the answer will be 1 by 4. So do you see, I mean, after doing all of this quantum mechanics discussion and everything, okay, I have these things. Yeah, go up there. Yes. So now do you see what has happened? The modes in a 1D channel, do they now depend
Yes,
on
sir, they are
energy?
constant.
Exactly. Therefore, for a 1D channel, the modes are independent of the electron energy. Is that clear?
Yes, sir.
So this is, I mean, one thing that I wanted to calculate today to show that this quantity, now this is a constant number, like our answer may be, depending on how we have defined things, like it is also possible to write this answer as 1. But the message that we want to take away from this is this quantity will not have any factor of E occurring in it.
Yes, sir.
So for a 1D channel, therefore, what will the current be? Which implies I, sorry, not E. I is equal to 2q upon h integral some constant into f2 minus
F1
f1.
minus F2.
Yeah, that's all. Is this clear now?
Yes, sir.
Yes, sir.
So now to answer your original question as to why we are not solving for the exact current value or current density value, the answer to that is we have to define f2 and f1 accurately. So for that we need temperature dependence and like every individual parameters, and I need to identify the material and so on and so forth. However, it is possible to do these things for certain particular combinations, and that will show up in the following weeks. So this part, as I mentioned before, will be covered in the coming weeks. Do not worry about it. As will the other thing that Ichanshu pointed out about carbon nanotubes being a 1D channel, that will also be covered in the subsequent weeks, where we shall look at quasi 1D and 2D. And so, question: can there be a quasi 3D system? Like I said, a quasi 1D system is a 3D system that is very large in one dimension and very small in two other dimensions. Correct?
Yes, sir.
A quasi 2D system will be very large in two dimensions and very small in the third dimension. Can we
Yes,
have a
sir.
quasi 3D system?
Yes, sir. If no, sir, because we cannot.
Yeah,
Uh,
because all three dimensions are large. If all three
huh.
dimensions are large, it's a 3D system.
Yes, sir.
Okay, so yeah, so later on in the weeks, you shall be looking at what to say, like quasi 1D and quasi 2D systems also, and they will also have what to say, like some applications for certain device designs that will be covered more towards the end of the lecture. But your numericals, like insofar as your assignments and your exam questions go, will be something along these lines. Like essentially, you'll be given a system. Now, as you can see, 1D, the answer is a constant. So, as you can guess, we will not be asking about 1D modes because it is a constant. Now, you can guess that 2D modes will now have an energy dependence because you know what the respective quantities are. Correct?
Yes, sir.
Okay, so it will have some kind of an energy dependence. So 2D modes is a more interesting question. So for 2D, you will have some questions, not in the coming assignment, but maybe in the assignments after that. You will be asked as to how many modes exist at a certain energy level or at a certain temperature, and these things. Of course, you will get the information on how to do the variable substitution. So those are the problems that you will get. In order to solve those problems, the steps that you have to follow are exactly the same as this. Let the board open up. Uh, Yeah. So for the modes calculation, you have to identify the density term, identify the broadening term, assume this, like you have to find out the average x velocity in the positive direction. Now, if it is a 1D electron, then I know that half of the electrons will be moving in the right direction. But if it's a 2D distribution, then the electron can in principle be moving in any direction. It can be moving, vertically also, it can be moving horizontally, it can be moving at an angle. So you are supposed to find out what fraction of those electrons are moving effectively in the positive x direction. So for that you have to do certain integrations. Those integrations will be demonstrated in class. Uh, or you know what? Let us do that next. Why am I leaving that out? We still have time. Let me do that next. So consider now we are not doing modes calculation. Now we are just doing velocity calculation because we have found out that if we know the velocity, we know the transition time. If we know the transition time, we know the broadening. Density of states we have already covered. We hopefully remember those quantities. So now let us just look at average positive velocity for a 2D channel. So how do we do this? So in a 2D channel, I will have two axes, correct?
Vx, Vy.
Okay, yes. So let me draw my channel first. I'm ignoring the source and drain for now. Okay, and I have W and L. So in here now electrons can move in any direction. Now how do we find out what the effective, how do we find out this quantity Vx plus average? How do we find this? First, as before, we will consider the kinetic energy relation. Now notice that I am not writing any coefficients here, I am just leaving it as V. This is equal to E. So here V is the speed, which implies V is equal to of course MSM star, like always effective mass. So I will be able to write this quantity over here. So V is equal to square root of 2E by N star. All right. Now what
Yes,
is
sir.
our assumption? V can be in any direction. Correct?
Yes, sir.
Okay. So at this point, I can have V going like this, I can have V going like this, I can have V going like this, this, this way, straight up, straight down. Now, which are the velocity values I need to consider to calculate this? How do I find that out?
Area.
Area of what?
Area of 2D channel. Like we considered some specific area.
Uh-huh. Okay. Like anything further to say to that, like some specific area? Or can I do this? First, tell me what Vx is in this. If velocity is pointing in some direction, how do I tell what Vx is? Vx is equal to what? I know the speed is v. I know this quantity. If this angle is
Sir,
theta.
Vx is velocity of electron in x direction.
Yes, so now if this is the direction in which v is going, so what is Vx now?
Sir, v cos theta.
Very good. So v cos theta. Now, essentially, to find the average x velocity of the electron, what do we have to do? We only have to consider those electrons that are traveling in the positive x direction. Now, if I start measuring my angle theta from here and go anti-clockwise, what is the range of theta for which the electron is moving in the positive direction? Just consider this line. This is theta equal to 0. So what will be theta at this point? Because any velocities in this direction are moving in the minus x direction. So I don't need those.
So 0 to pi.
Very good. 0 to pi, or like what is the angle at this point? If this is 0, this is theta equal to 0. Horizontal is theta equal to 0.
Yes, sir. If horizontal is theta is equals to 0,
Uh-huh.
then 0 to pi.
Is this angle pi? Is this angle at this point? Is that pi?
Sir, please point it out again.
This direction. Let me see. This is theta equal to 0. What is the angle when I come to this direction? Like
Sir,
see, in this
pi by
half,
2.
yes, this half is the half that I care about. Electron velocities in this half is the only half I care about. Okay,
Then 0 to pi by 2.
but the bottom half should also be considered. So minus pi by 2 to pi by 2, because even these electrons with speed in this direction will have a positive Vx. Is that
Yes, sir.
clear?
Yes, sir.
So yeah, the integral, this integral will
Minus
therefore
pi
be
by
written
2 to
as
plus pi by 2.
yes. Exactly. Vx plus is now equal to integral. So this is the formula for average v cos theta d theta divided by integral d theta. So the limits of the integration is minus pi by 2 to pi by 2. Likewise, pi by 2 and minus pi by 2. So what is integral v is a constant. So what is integral cos theta from minus pi by 2 to pi by 2?
Sir, 2.
Very good. So this is equal to 2v. What is the denominator?
Sir, pi.
Very good. Okay. Now is that clear?
Yes, sir.
So this is the average Vx for a 2D channel. Now tell me what is the transit time.
Sir, L by Vx.
Average, like mean Vx. So yeah, so tell me what that answer is. It is L into pi by 2V, I suppose. Correct?
Yes, sir.
Now tell me what is gamma E?
Sir, h bar by tau.
Yes. So that is what?
Sir, 2V h bar by L pi.
Very good. 2V by L pi. Ah, okay. Yes. Now we shall. So, are you guys familiar with this quantity known as the de Broglie wavelength or the de Broglie wavelength?
Yes, sir.
What is it? It has the symbol lambda b. What is lambda b?
Sir, lambda b of de Broglie wavelength.
Yes. So the formula is given by h by p, where p is the momentum.
Yes, sir.
That is equal to what? That is equal to. So let me write this in red just to distinguish. So lambda b is equal to h by p, which is equal to h by m star v. Okay.
Yes, sir.
So yeah. So what is this quantity then? What is 2v? Can you write it in terms of the de Broglie wavelength?
Sir, if we convert this uh, h into h bar in our de Broglie one relation,
Forget that.
then
For now, just write v in terms of lambda b. H and h bar we will take care of later. Just write v in terms of lambda b. And the expression is right here. Just tell me what v is in terms of lambda b.
sir, VA equals to h by lambda b into m star.
So this would be. Wait, I'm actually making a small mistake somewhere. Yeah, I'm actually making a mistake somewhere. Gamma E is h by tau. So yeah, somehow I am messing up somewhere. Just give me 1 second. I've actually made a small mistake. Up until here, we are good. Essentially, I should be getting. Yeah, I should be getting an inverse wavelength term, but I'm getting a direct wavelength term. Where am I messing up? Up until here, everything is good. The average velocity has been calculated correctly. Um, just 1 second, let us sort this out. Let me get rid of these things and let me simply write the final answer to the right here to v by pi, and we can just define lambda b as h by m star v, and then v v and then right gamma. Oops. Is equal to, why is that happening? Of course, that is happening. I'm sorry. Yeah, I'm really sorry. Of course, that is happening. Yeah. So, no mistakes. So, gamma of E, as we saw before, was h bar 2v upon pi L, correct?
Yes, sir.
Good. Now, let us go ahead and calculate what uh, M of E is for a 2D system. That is what? That is d to d of E into gamma of E, correct? Gamma of E by
Yes, sir.
2 into pi, right? Into pi, correct?
Yes, sir.
So I've given you all the values. What is d2 de? M star by pi h bar square into L into W multiplied by h bar v by pi L into pi, correct?
Yes, sir.
So now let us cancel all the relevant quantities. So this pi and pi cut out, L and L cut out. Okay, one of this h bar gets annihilated. So I have another free pi, and so this is equal to what? This is equal to m star v divided by pi h bar, correct? Into W.
Yes, sir.
Now change the h into h bar. Go ahead. H bar into h. Be my guest. So what will that quantity be? If I change h into h bar, this will become h by 2, correct?
Yes, sir.
So what is this quantity then? m star v by h. What is that?
For m star v will be our momentum. So now we can uh, replace it by de Broglie wavelength.
Very good. So that will be equal to 2w by lambda b. Is this correct?
Yes, sir.
Yes. Or in other words, it can be written as by 2. Correct?
Yes, sir.
So for a 2D channel, somehow the number of modes is directly related to the width of the channel and the de Broglie wavelength. In fact, what does it say? It says the number of modes is exactly equal to the number of half wavelengths that can fit into the width. Is that clear? Can you see that? Is that clear? Can you guys hear me?
Yes, sir. Yes, sir.
Yes,
So,
sir. Yes, sir.
yeah, this is the second result. This is also a very important result. And unfortunately, by doing this, I've actually solved a lot of your assignment questions. So, enjoy. All right. So, I thought I would not do this, but well, we have time and something has to be done, and this is a good thing to illustrate. So, as you can see, the number of modes does not depend on the length of the channel anymore. It depends on the width of the channel for a 2D channel and the number of half de Broglie wavelengths that is fitting into that width.
Yes, sir.
So now
Yes,
can
sir.
you see that how the wave nature is showing up in ballistic transport? Remember, I told you that yes, in
Yes, sir.
ballistic transport we are actually considering the electron as a particle, but some wave nature is there. That wave nature is now made apparent in this expression. I'm not writing this out separately to show what it is because again this is important for the lectures. So I'm going to leave it like this. People who see the video can, are who listen to 1.5 hours of the video can benefit from this. I'm not going to explicitly write it so that
Yes,
people
sir.
who, read the slides directly take it. So this is for a 2D channel. So this is the number of modes at a given energy. So now, of course, V depends on E using this relation, right? And from
Yes, sir.
that, you can substitute and find out the de Broglie wavelength and divide W, the channel width, by that, and then you will get your number of modes. So it is like, yes, previously when we saw the modes, we used some quantum mechanical arguments, and we spoke about density of states, we spoke about energy broadening, Heisenberg's principle of uncertainty and everything. But at the end, after doing all the calculations, it just comes down to calculating the de Broglie wavelength and dividing the channel width.
Yes, sir.
So there is a certain
Yes,
simplicity to
sir.
finding the modes. I will encourage you to do this for a 3D channel and see what happens.
Okay, sir.
Okay,
Okay,
because
sir.
most likely there are no questions based on that in the assignments. Even in your exam, I don't think such questions will appear. But for your own, interest and practice, you can follow the same method. Like everything we have discussed so far, is the exact same method. Of course, this integral will change because now there will be 3 dimensions. There will be an L, a W, and a depth, a D. So that will also show up. So think of what happens there in terms of those quantities. if you want to. Again, it may not directly benefit you in the course, but it will be a very good learning experience. Okay, so that is
Yes,
the
sir.
second part that we are covering. So yes, so now okay, let us do a small numerical to see what happens. Okay, so consider, so for a 1D channel, modes are somehow constant. 2D channel, it is this. So now consider a 2D channel of width how much shall we say, 5 nanometers. Okay, find the number of modes and what energy shall we consider? Tell me some energy. Shall we say 10 electron volts? Like as you can see, I'm making up this problem right here. So yeah, let us
Yes,
say
sir.
10 electron volts. Okay, and assume m star is equal to m for an electron. M star is equal to me. So can you calculate and tell me what happens? Or at least can you walk me through? Like, don't do the calculation. You guys tell me how the answer will go. I've given you the energy. I've given you the mass. I've given you W. So tell me how to calculate de Broglie wavelength from energy. Just tell me the formula. You
Sir,
don't have to give me the answers.
from energy, if we consider it to be kinetic energy,
Yes.
and then we convert it into momentum,
Yes.
then we will be able to find the Broglie wavelength.
So give me the formula for momentum in terms of kinetic energy.
Sir, half
Yes.
PV, kinetic energy equals to half PV.
Why not keep only momentum? Why are you having an additional velocity term? Ultimately, I just need momentum. So can we
Yes, sir.
write kinetic energy is equal to p square by 2m?
Sir.
Huh. So that implies p is equal to square root of 2me.
Yes, sir.
M is m star. Okay. So let us substitute that. It is 2 into 9.1 into 10 to the power minus 31 kilograms into 10 into 1.6 10 to the power minus 19 joule. So it is this quantity. So if you have a calculator at hand, I mean, feel free to join me. I will also use a calculator that I luckily have to calculate this quantity. Yeah. So this comes out to be
17 into 10 raised to minus 25.
yeah 1.7 into 10 to the power minus 24. What is the unit of momentum?
Kg meter per second.
Very good. Kilogram meter second inverse. So what is the de Broglie wavelength? H by P. What is H? 6.62 10 to the power minus 34 divided by 1.7 into 10 to the power minus 24. So luckily, powers are pretty nice. So it is essentially 6.62 divided by 1.7, that is 3.9. So
Yes,
this
sir.
comes out to be 3.9 into 10 to the power minus 10. And just to make ourselves, uh, more comfortable, I shall say this is 0.39 into 10 to the power minus 9. What is the dimension of this
Nano,
quantity now? This is
Uh, Nanometer.
0.39
in
nanometer.
meters. So now this becomes approximately 0.
0.39 nanometer.
0.4, like approximately nanometer.
Yes, sir.
Okay. Now, what is the number of modes?
Sir,
Is
W
equal to,
by lambda V by 2.
yes, 5 divided by 0.2. What is that?
So 25.
Very good. So at 10 electron volts, we will have 10 modes for electron transport in this 2D channel. Now, I mean, as you can see, I did not prepare this problem beforehand. I just chose two random values. But you can see they seem to be agreeing somewhat harmoniously.
Yes, sir.
Okay,
Mhm.
so that implies
Nice.
these values are somewhat reasonable. This assumption is okay. If there is a 5 nanometer channel, then maybe energies, maybe it may not be 10 electron volts, but it is only going to be of the order of a few electron volts. Had I taken 1 kilo electron volt, then I would have gotten something like, I don't know, um, of 3000 modes, and that usually means that I don't no longer have ballistic transport. When I have those many modes, things like scattering are bound to happen. So you'll understand why that is the case as you listen to the lectures. I don't want to get more into those details yet, but this is a numerical to give you the flavor. And as you can see, for this precise reason, we cannot have any numericals for the 1D channel because it is a constant. Okay,
Mm,
so I encourage you to try out things for the 3D channel. So number of modes is yes, 25, which seems to be very. It's a nice round number. So now we can essentially, when I say that an electron of this much energy is moving through a ballistic channel of, and again here we are not talking of, we have not mentioned anything about the length of the channel. Okay, so now can you guess what the length of the channel should be?
infinite, sir.
Infinite.
For 2D material, na?
Yes. See, this is W. What is L for the channel? Now, this is not a numerical question, by the way. You can try doing some numerics, but this is not numerical. Use your concepts. Remember contents from week one. There is an assignment question in week one that answers this. When will you have ballistic transport? When the channel length is what, very large compared to the de Broglie wavelength, or very small, or approximately the same?
Sir, large than the Broglie wavelength.
How large? Very, very large or slightly large? So let me ask you this. Is, oops, sorry, is, uh, what has happened? Yes, yes. L equal to 300 nanometer valid for ballistic
Sir,
transport.
very very large because uh, if if it is matlab small in if it is in nanometers only,
Uh-huh.
then it will be considered a quantum transport.
Uh-huh. Okay. So now this is my question. And next question is same question, but is L equal to 10 nanometer valid? Which is more valid, 300 nanometer or 10 nanometer?
10 nanometers, sir.
Why is 300 nanometer not valid?
Okay. Hmm.
So essentially, what happens is as the channel length becomes larger and larger and larger, the probability of collision and scattering increases.
Rating is
So,
high.
yes, so ballistic is a limit where I'm close to the quantum limit, not too far away. I'm close to the quantum limit. So I know that my de Broglie wavelength is around half a nanometer. So this is around 20 de Broglie wavelengths or 25 de Broglie wavelengths. So up until that, it's kind of okay. It's fine. Beyond that, maybe there will be problems. So again, the connection as to when I will have ballistic transport, when I will have diffusive transport, this part will be covered in the week 5 lectures. I do not want to go into those derivations because then I will be repeating the content. Please study that and try to find a more clear answer to this. And in case you guys attend next week's discussion session, I will be very happy if you can, give your answer and your views for these two uh, cases, channel lengths. Okay, I
Yes,
would
sir.
really
Yes,
welcome
sir.
it. Okay. So, yeah, with that, I think I don't want to do anything more because we have actually done two somewhat detailed derivations and, one basic introduction to the concept of modes and whatnot, and one, okay, simple numerical, but that explains the concepts. I hope the concepts are clear based on this. Any questions on what we have discussed today? In this session, any clarification, anything that you want me to revisit or cover again or emphasize before I finish and summarize today's discussion?
Sir, not from today's session,
Ah, please,
but
anything from
from
previous also, go ahead,
uh,
please. Yeah.
but from week 4 assignment question number 10.
Okay, let me quickly open that. So, week 4 assignment 4. So again, like if you have doubts with the previous assignment questions, like you can ask right at the beginning itself, no issues. So yeah, here we are at 10. Yes, consider the diagrams below where Ne is the density of states and Fe is the Fermi function. uh, the diagrams show Ne and Fe plots for three materials. The Fermi level is represented by the dotted blue line. Which of the following is a 2D material doped by donor atoms? Okay.
So, sir, I went with option number B.
Uh-huh.
Because if they are donor atoms, then it goes for N type, and for N type we get the graph as in figure B. But I'm not able to get why it is none of these.
So see, there are two
Sir, can I
things.
suggest something?
Please go ahead, by all means.
Yes, sir. Yes, sir. Actually, while solving this numerical, I also selected the option B. But
Uh-huh.
when I go through the density of states derivation, That for
Yes.
2D material that is constant. It's
Yes.
constant, sir. So all these three options are not valid in that case.
Very good. That is the answer. You have it.
Yes, sir.
Is that clear? Yes, the Fermi function is correct for option B. You are correct, 100%. But it is a 2D material with donor atoms.
Yes, sir.
So technically speaking, this I should have had two straight line scoops, two straight lines over here, not a curve. I should have had a vertical line here and another vertical line here. That would have been the correct answer.
Yes, sir.
All right. So any more questions like from this assignment, previous assignment? Any queries, doubts, please go ahead and ask. And a vast majority of our questions will be of this kind. Like there will be numericals, yes, but at least in our group over here, like since I'm working under the instructor for this course, I can say that with a certain amount of confidence that more so than solving actual numericals, our aim is that the people who are attending this course understand the concepts. So when someone says, modes in a certain channel, they should be able to at least visualize the concept. Even if they are not remembering the formula, they are not, in fact, the modes formula I did not remember today before the session. So in the 5 minutes that I waited before starting this session, I had to go and revise those expressions. I had forgotten it because it has been a while since I had revised these things. So that part I did not remember. But this later part, the part about the de Broglie wavelength, of course I remembered. That is why I got confused in between because I knew that ultimately the answer should be some length divided by lambda b. But initially, when I was just looking at the transit time, it was not looking like that, and so I got confused. Then I was like, okay, fine, I have to do the complete mode calculation. So that much I knew. So that is exactly what will be expected from you guys also. You need not remember the derivation. You need not even remember the complete, expressions or integrals or whatever in many cases. But you have to understand what the approximate energy dependencies are, how certain functions will look at certain temperature conditions. If I say T equal to 0 Kelvin, how will the Fermi Dirac distribution look like? If I say T equal to 0 Kelvin, how will certain density of state functions look like? So these are things that we will expect the attendees, the students to, or as NPTEL calls it, the learners to understand. Okay, so all right, yeah, that is what I had to say. Any further questions or queries, please? Anything in this assignment from the previous assignment? Anything other than assignment 5? I'm happy to answer.
No, sir.
Okay, all right. That is good actually. I mean I mean I hope that is good because that means you guys understand things more or less. So I'm stopping the presentation. So yeah, uh, that kind of brings us to the end of today's session. I hope it
Thank you,
was
sir,
of
for the
some
time.
benefit to you guys. Yeah. So again, like I have posed some questions. If you are interested, you are free to work those things out. I encourage you to do whatever we have done for a 1D and a 2D channel for a 3D channel and see how things change and evolve. And in fact, if you can go further and do the de Broglie wavelength comparisons, you will see some interesting things because it is not going to be covered in the course. That much I can assure you. It is not a part of the syllabus. But if you do it on your own, you might actually see some interesting things, and it might trigger your curiosity about these concepts. So I heartily encourage you to do that. So that is all for this week's session. We will meet again same time next week. I thank the both of you for joining in and listening and interacting with me. So we shall see again next week.
Yes, sir.
I
Thank you, sir.
am,
Thank
yeah,
you.
ending the
Sir,
call.
can you
And
share the link of the recording?
yeah, so I will put it up on the. So you guys have access to the course forum, right?
Yes, sir.
Yeah, so I will put up the links on the forum for all of these things, including this session, which I will upload right now, because I have to
Yes,
like
sir.
upload this to YouTube and do those things. So I'll upload it and I will share the links to you guys. Okay.
Yes, sir.
I
Thank you,
think
sir.
once
Yeah.
you upload, we'll got mail, na?
Yeah, you should get a mail from the notification forum. Yes.
Yes. Yes. Thank you, sir.
Yeah. Yeah. Yes.